Welcome to 1 and Day 18 for Math 360. We're going to be talking about the gamma distribution and the chi-square distribution. For this purpose, I wanted to introduce the idea of the gamma function. So the gamma function is defined to be, this is the Greek capital letter for gamma. Gamma of t is equal to the integral from 0 to infinity of y of t minus 1 e to the negative y dy, where t is greater than 0. This relationship is the generalization of what you're maybe familiar with, the factorial function. We're going to explore that relationship a little bit and then tie this back into the gamma distribution and the chi-square distribution. Okay, so suppose for a second that t is not only greater than 0, but is actually strictly greater than 1. Okay, then we can do a little bit of fun here. So we can take the definition of the gamma function and use integration by parts, simply by letting u equal y to the t minus 1, differentiating that, we get du is equal to t minus 1, y to the t minus 2 dy, and then dv will be e to the negative y dy. So integrating that, you get negative e to the negative y. Okay, so if we plug in uv here, we're going to get negative y t to the minus 1, e to the negative y, evaluate from the limits of integration, minus, and then this minus and the minus from here, from the dv part, will cancel out, but I'll just plug everything in directly. So this is du v dy. Okay, now notice, like I said, this negative and this negative are going to cancel out, and the t minus 1, with respect to this integration, is a constant, so I can actually factor out this negative and all of this coefficient out. And we'll change the sign here, and then let's look at the limit here of integration, the limits of integration here, to see what value that is equal to. Okay, and so if we pull everything out, rewriting everything. Let's see if I can maybe squeeze it in here. Okay, let's evaluate the limits here and see what's happening here. So in the limit, as we have y going to infinity, we have the negative we can ignore, but this is y to the t minus 1 over e to the y. Now remember, y is strictly greater than 1 here. So this is like y to the, and let's say t is 1.1, then this would be negative y to the 1.1 minus 1, or y to the 0.1. Or t could be something really big, like 10,000. This would be y to the 10,000 minus 1. This number can grow really, really big. However, its rate of growth is going to be squashed by this exponential function growing in the denominator. And so as y gets really, really, really large, t is greater than 1, and this whole thing then is going to tend to 0. Okay? And for the second one, this is for the upper limit of integration. So we have minus, then the lower limit of integration. Well, e to the y, sorry, yeah, e to the y is 1 when I plug in 0. And I have that divided by 0. So this actually just will equal 0. So in short order, what we see is that this entire quantity equals 0, evaluated at the limits of integration. And dealing with this, then, as mentioned earlier, taking out the common factors there, that's going to become a plus the integral. Oh, let me try that again. It would be plus t minus 1, factoring out the whole thing there, the integral from 0 to infinity of y. Oh, there should be a 2 here. And wrote a 1, there should be a 2. Okay, y to the t minus 2, e to the negative y dy. Okay, so let's rewrite this whole line then and notice something here. We have the integral from 0 to infinity of y to the t minus 1 e to the negative y dy. And what is that equal to? It's equal to t minus 1, the integral from 0 to infinity of y to the t minus 2 e to the negative y dy. But if we look at if we look at this part right here, isn't that just the definition of the gamma function? Isn't that just the definition of the gamma function? Maybe I can write it a little bit more suggestively. This is this is t minus 1 times the integral from 0 to infinity of y to the t minus 1 minus 1 e to the negative y dy. And so this relationship right here uh, looks very much like the gamma function, just one less. So if this t had just been, if it was the gamma of t originally, right? This part right here, this is the gamma of t. This is gamma of t by definition. Then this looks like exactly gamma of t minus 1. And so you get this interesting relationship that gamma of t is equal to t minus 1, gamma of t minus 1. Okay. And then this should ring a bell to what I meant when I said that this is the generalization of the factorial function. So if t happens to be, for example, if you let t equal, let's say 4, and then gamma of 4 is equal to, well, what is this? This is 4 minus 1, so that's going to be 3. And then if we did it again, we're going to get 2 and then 1. And so this is exactly the relationship. If we did this 3 times, that the generalization of the gamma function, uh, or sorry, of the no, what am I thinking of? The factorial function, there it is in fact the gamma function as shown here. So that's a really cool consequence. The gamma function has several other nice properties, some really cool things, but this is important directly to our work looking at the two distributions we're discussing in 1 to 18. Okay. All right, let's jump over to that and consider some more information in that. All right, so this whole distribution process gets its start if we remember back to when we jumped into waiting times and counting the number of flaws. This is a generalization of the Bernoulli principle. So we're talking about a Poisson process, which has a mean lambda, and we were first working with this in the discrete case, waiting for the number of times until the first error occurred, and then we talked about in the last section about the continuous version of this with respect to waiting time, which was a continuous variable. Okay, so in the last section, we talked about the Poisson distribution with respect to the first waiting until the first error occurred. Okay, and that was the exponential distribution. So that's what we talked about last time. And so now we're going to let W equal the waiting time again, but we're going to consider when there are multiple errors. Okay, or until we're going to count more than there. All right, so just like last time, we're going to let W has a distribution. We're going to let W be greater than or equal to 0. If W is less than 0, then the probability of the distribution function is equal to 0. Okay, so let's consider some distribution function of W. And we want to know for when the time is less than or equal to the number of minutes or hours or seconds or whatever units or time we're measuring. And so we know that that's equal to 1 minus, this is the complement, right? So this is the number of, what is this? This is the number of, and then I didn't have enough room here for this. And this is uniquely me. I tend to have coffee stains on every piece of paper. So if it doesn't have it, I didn't touch it. Okay. So we have 1 minus P. And so what is this? P greater than, or where P of W is greater than W refers to the fewer. This is 1 minus when the number of alpha have occurred and is fewer than that value on 0 to W. Okay. So we have the number of changes that we're counting, which is alpha, is less than that number on the interval from 0 to W. Okay. And we saw that this value is expressed counting the errors from the exponential as lambda W to the K, e to the lambda W over K factorial, and we're summing over the results, of course. Okay. And so the number of changes on the 0 to W has a Poisson distribution with mean lambda W, and W is a continuous type. So that's important because that tells us then that f of W, if it exists, okay, so the derivative have to exist there, is the PDF with W greater than 0. And if that's the case, then we say that f prime of W is equal to lambda a times lambda W e, not e, sorry, alpha to minus 1 e to the negative lambda W over alpha minus 1 factorial. And then it's also important to note that when W is less than 0, we define that the distribution is 0, and so also the derivative would also be 0. Okay, so this is the gamma distribution. We're going to explore a little bit more detail here. Okay, so let's explore this a little bit. W, that's the waiting time until the alpha change in a Poisson distribution. Then if that's the case, so that's what we're looking for. And we say that has a gamma distribution with the parameters, with the parameter. Yeah, that's awesome. Alpha and theta equal to 1 over lambda. Then the given PDF, if we think of this in terms of x, just as a placeholder, we typically write these as f of x's. Then f of x is equal to 1 over gamma of alpha, theta to the alpha, x to the alpha minus 1, e to the negative x over theta, where the support is between 0 and infinity for our random variable. Okay, and let's check that this has the properties of the PDF. So first of all, note that it's definitely positive, and f of x is also positive. And if we consider the integral over all space, since the distribution is 0 when f of x is less than 0, we have this is the case here. And so once we compute those results, x to the alpha minus 1, e to the negative x over theta, if we look at this distribution and make a substitution, change of variables, if you will, and just let x equal theta y, for example, note that dx is equal to theta dy, and then we substitute those values in, you get theta y to the alpha minus 1 over gamma alpha theta alpha e to the negative y. The thetas cancel, and then I have a theta and a dy left over from the change of variables here. So just a note on the algebraic side of things, right? You have a theta. We're raising an exponent to an exponent, so you multiply these together. You have a 1 on both of these. So it's going to be alpha minus 1 is the power on theta. So one of the powers gets taken up here. If you multiply like bases, you add exponents, and so negative 1 plus 1 will give you 0 there. So now you have a theta to the alpha, which cancels with theta to the alpha in the denominator. And then you have a y minus 1, or no, sorry, a theta minus, wrong letter, an alpha minus 1 for the exponent on y. So now, and this is one of the things that's fun about these gamma functions, is they show up in random places and in different ways. We just have to be looking for or pay attention to the form of the integrand. And so here you have 0 to infinity, y to the alpha minus 1, e to the negative y dy. Well, this is the exact definition of the gamma function. And so this alpha gamma function with alpha here, it's a constant with disruptive integration. So I can pull it out in front, or I can compute this and then divide by the value of this alpha gamma function. And so what you see here is that this is actually exactly this. This is gamma of alpha. And so we have gamma of alpha divided by gamma of alpha, which means that indeed, when you integrate over all space for this PDF, the likelihood that something will happen is 1. All right, so it definitely satisfies the properties of the PDF, which is also great. And now for the main star of our show, it happens to be a special case of this gamma distribution. It's a star because of its practicality, its use is so widespread in statistics. It has its own name, even though it's just a special case of this gamma distribution. And so let me introduce, I'd love to introduce with a drum roll thing, the chi-square. So in a special case, when theta is equal to 2 and alpha is equal to r over 2, then the PDF comes of this form. So it's 1 over gamma of r over 2, 2 to the r over 2. And then we have x to the r minus over 2 minus 1 and e to the x over 2. And the support here is still the same. I just didn't have enough room, but it's from x is less than infinity. So the support doesn't change. We call this distribution a chi-square distribution of R with R degrees of freedom. And so all the properties about, I think you'll be asked to compute the moment generating function and the mean and variance of this distribution. All those things come directly from the fact that they come from a gamma distribution. So those results shouldn't be too surprising. They are, in fact, directly related to the mean and variance of the gamma function. But I think it's a really cool consequence that all of these ideas kind of are tying together. And these distributions are all based on the Poisson process, which is a generalization of the Bernoulli process. So some really important threads to keep in the back of your mind as you're tying together these different distributions and what they're modeling and how they're paying attention to. Okay, time to get into some examples and look at some of the other fun things that come with these distributions and the types of problems that we can. Anyways, I hope that was helpful, and I look forward to seeing you in the next video.